Welcome, and thank you for joining this webinar, Invisible Power, Infinite Scale, How Ambient Energy is Pushing the Battery-Free IoT World, prepared by Alpert research team. That brings us to the software side, to intermittent computing. We've established that shutdowns are inevitable. What's the biggest risk when your computing is constantly being interrupted by power loss?
The biggest risk is just wasted work. If your device is in the middle of a complex calculation and the power drops below that V-off threshold, everything you've done up to that point is just gone. Without a proper system, you could get stuck in a loop forever and never complete a complex task.
And this is where checkpointing and task decomposition come in. They're the essential safety net. How do they work together?
So first, you have task decomposition. You have to break your application down into tiny atomic tasks. The output of each tiny task is immediately saved to non-volatile memory, NVM.
So its progress is safe.
Its progress is safe. Then, checkpointing is the reactive mechanism. The system is always watching the voltage. When it predicts a power failure is imminent, it triggers a checkpoint. It saves the entire operational state, all the registers, the program counter, everything to that NVM.
So when the power comes back, it can just pick up right where it left off.
Exactly where it left off. It's the only way to make forward progress across dozens or even hundreds of power cycles.
But checkpointing is reactive. It's a last-ditch save. The real intelligence is in being proactive, which is energy-aware scheduling, or EAS.
EAS moves that intelligence right into the operating system. Instead of just running until it dies, the scheduler makes smart decisions about what to run and when to run it. It looks at three things: how much energy it thinks it's going to harvest, how much energy it has right now, and what the task priority is.
So it's constantly making trade-off.
It might see that a low harvest period is coming and decide to defer a low-priority task to save power for something critical later on. It's managing its energy budget proactively. How does the system achieve this intelligent decision-making?
It starts with task decomposition. Complex applications are broken down into atomic tasks, each assigned dependencies, execution time, and priority. These tasks are then managed by a scheduler that is coupled with an energy predictor. The goal of EAS is to avoid execution timing that leads to a brownout, so when the voltage drops below V-off, thus minimizing wasted work.
This sounds incredibly complex for a simple microcontroller. How is the optimal timing determined?
Advanced EAS often relies on powerful mathematical frameworks. This framework models the system dynamics, the probability of energy availability, and the reward of task completion, and is used to maximize the long-term average reward, which is the task completion rate, while actively minimizing power failures. And crucially, the complex modeling and optimization are often done offline or in the cloud. The tiny microcontroller then just executes a much simpler, pre-computed optimal policy.
And this is where we can bring in a key finding, with credit to the Alpert research team.
Okay.
One of their reviewed studies demonstrated that an energy-aware scheduler can completely avoid power failures and achieve perfect performance if it has perfect knowledge of the energy it's going to harvest in that window.
Which is impossible in the real world, but...
But it sets the theoretical benchmark. It tells designers exactly how important and how accurate their prediction models need to be to get close to that ideal performance.
So how do you formally optimize this? It sounds like an incredibly complex problem.
You frame it as a mathematical problem, specifically a Markov decision process, or MDP. The MDP is like a smart decision engine. The state of the system is the capacitor voltage and the list of pending tasks. The engine's job is to choose the best action-run task, or sleep, to maximize the long-term completion rate.
And what does the analysis of that optimal policy show?
The optimal policy always has a threshold-based structure.
Can you give us an analogy for that?
Think of it like a smart driver deciding when to merge onto a busy highway. The driver doesn't just go whenever there's a gap. They only attempt the merge, which is like a risky high-energy task, if their gas tank, the capacitor voltage, is above a certain level.
And that level isn't fixed.
The threshold moves. If traffic is light, if the sun is shining and energy harvesting is high, the threshold is lower. You can be more aggressive. If traffic is heavy, a cloud passes over, the threshold shoots up. The system becomes very conservative and only does the most essential things.
And this energy awareness has to go all the way down to the individual task level, with per-task budgeting.
The system needs an accurate estimate of the energy cost of every single operation. This allows it to do things like dynamically reorder tasks. An accurate estimate is what prevents those mid-task brownouts.
And based on these budgets, tasks get sorted into different categories. What's the difference between a capacity-constrained task and an intermittent one?
An intermittent task is easy. It's low energy and doesn't mind being paused and resumed. A capacity-constrained task is a high-risk operation. It needs a minimum amount of energy to be completed in one go without interruption. Then you also have temporally constrained tasks, which are reactive things that have to happen now, no matter what the energy state is.
And this even extends to the outputs, the actuators. How does energy-aware actuation work?
Actuators, motors, displays, LEDs can be huge power drains. So the system applies the same predictive logic. An e-ink price tag on a shelf might defer its screen update until the store lights are brighter, or, more cleverly, it can modulate the intensity of an action.
So instead of a simple on-off,
It might reduce the torque of a servo motor or dim an LED, just enough to guarantee the action can complete before the capacitor runs out of power. It's trading a bit of performance for guaranteed completion. I think the key strategic takeaway is that shift in market dynamics. This technology fundamentally transforms what used to be an operational cost for a network operator, blasting out a radio signal, into a monetizable service, providing wireless power. This movement creates new ecosystems where the manufacturers and retailers who actually own the sensor data become the new data hubs. They create value in a way that's separate from just providing connectivity. It forces a total reassessment of where value lies in the entire IoT chain. Interested in gaining a deeper understanding of the transformative power of wireless technology? Join the Alpert research team's webinars to explore cutting-edge wireless innovations, their applications, and their implications. Click the links below to learn more.